in this video, we're going to be talking about permutations and combinations and the distinctions between them and circumstances where problems like involve permutations and problems involve combinations. All right, so let's get started with permutations. So a permutation is an arrangement of objects in a specific order. This is very important. The order is specific, the order matters. So let's say I have n different things and I'm trying to permute them, I'm trying to reorder them. Then the number of permutations or number of reorderings is n factorial. And n factorial, just to refresh, is n times n minus 1 all the way until 1. Okay, so P of nr, that's how we say this, P of nr is equal to n factorial over n minus r factorial, where P of nr represents the number of permutations of n objects taken r at a time. Okay, so for example, how many ways can we arrange 3 out of 5 books on a shelf? So let me just call these books like, I don't have any fancy names, but I'll just call them like B1, B2, B3, B4, B5. Okay, so I have 5 different books, right? And like the formula is P 5, 3, P of 5, 3. Again, I actually rarely use this notation, but it's something that's good to know. But why is this even true, right? So I gotta first pick my first book. So there's 5 books to choose from. So, okay, 5 books. Let's say I picked the second book to be first on my shelf. Okay, now I have 4 books remaining. Let's say I picked the 4th book. Okay, so now I have 2 more books I can choose from, right? Sorry, I have 3 more books I can choose from, right? So I have 3 choices here. And let's say I pick the first book. So as we can see, like the book's arrangement on the shelf, like I actually care about it. So I'm not going to do any correcting as I did in the past. I'm just going to multiply them together. So this is equal to 5 times 4 times 3, which is 60. Okay, and you can use this P of 5, 3. All right, so let's go over a few examples. This one should be familiar. How many ways can we arrange the letters in the word cat? Okay, so I have 3 letters, right? So there's 3 possibilities for the first letter, 2 possibilities for the second letter, and 1 possibility for the third letter. So this is just 3 factorial. You don't have to write that, but I just wrote it. But when you multiply them out, you get 6. Okay, next problem. How many ways can we arrange 4 out of 6 students in a line? Okay, so there are 6 different ways to pick the first student, and then 5. And now we've picked 2, so there's 4 left. And now we pick 3, so there's 3. Okay, so 6 times 5 times 4 times 3. I think this is 360. Okay, do notice that this is P of 6 comma 4, which is equal to 6 factorial over 6 minus 2 factorial. If you like, you could verify that when you actually calculate this, it's equal to 360. Okay, next one, problem 3. How many different 5-digit numbers can be formed using these 5 digits without repetition? Okay. So like, right, so I have 5 different places. And It's like 5 digits, right? So there's five, like the number is 5 digits, and I only have 5 digits to use, right? So what that means is that I need to use every single digit exactly once. Every single digit exactly once. Okay. So that's like important, I guess. So let me just like, just do this method and like fill out how many ways I can place each digit. So I have, let's just say I have 1, 2, 3, 4, 5. Okay, so how many ways are there for me to place this digit? There's 5 ways, right? I could literally choose any of them. So there's 5 ways. Let's say I choose the digit 3. Now I have 4 choices left. Let's say I choose 2. Now I have 3 choices left. 1, 4, and 5. Let's say I choose 5. Let's say now I only have 2 choices left. So let's say I choose 4. And then now my last value is basically guaranteed at this point, like just 1. Okay, so the number of ways I can do this is 5 times 4 times 3 times 2 times 1, which is equal to 5 factorial. Again, if you want to use that notation, you can write this as P of 5 comma 5. All right. Next question. How many ways can we arrange the letters in the word balloon? So this does involve permutations, but there's like some subtlety to it, right? Like if we did not care, like if we're somehow able to tell that this O is different from this O, and if we're somehow able to tell that this L is different from this L, then yeah, then the answer would just be there's 7 letters, so it'd be 7 factorial, right? But we do need to make our corrections here. There are 2 of these letter L's, so we can arrange those letter L's in 2 factorial ways. And there's 2 of these letter O's, so we can arrange those in 2 factorial ways. So after making our correction for these, we get 7 factorial divided by 2 factorial times 2 factorial. Now, here's like a fun fact. There's only one of these letter N's, and there's only one of these letter A's. There's only one of these letter B's. So there's like 3 letters with only ones, right? If we want to also divide by 1 factorial a couple of times, like 3 times, like 1 factorial is equal to 1. And actually 0 factorial is equal to 1 too, which is another important detail. But if we're dividing by 1, we don't really change the result in any way. Okay, so that is how we solve this problem. All right, now we're going to talk about a related topic, but slightly different. These are called combinations. We have pretty much worked with combinations in the past, so this will be like something very, very similar. So let's say that I want to pick our things, like our objects, from n distinct objects. Then like in this regard, right, like I do not care like what order I choose them in. Like I don't care at all about that. So the number of ways I do this is given by this formula right here. So this formula right here is n choose r. Okay, so in English I say it like this: n choose r. Why? Because I'm choosing r things from n things. This is like, in my opinion, the most common way in which people write it. Like it's my preferred way of writing it, but you'll also see people write it like this. You'll see people write it like C of n comma r. You'll see people write it like this. You'll like NCR. Yeah, you'll these are other 2 different ways to write it. Okay, so let's say I want to see how many ways I can choose 3 books out of 5 of them. Then the number of ways is just 5 choose 3, and I use this formula for it. 5 factorial divided by 3 factorial, 5 minus 3 factorial, and when I expand that, I get 10. One caveat about expanding it, you can save a lot of work when you're expanding it. Okay, so 5 minus 3 is 2, so 2 factorial. So I could actually calculate 5 factorial, like 5 times 4 times 3 times 2 times 1. And if you like just memorize that, that's okay, it's 120. But for larger numbers, it'll take a lot of time to actually calculate. So like, yeah, I could do 120 divided by 6 times 2, and I'd still get 10. But here's a better way to do it, especially for larger numbers. 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1, and then 2 times 1. So notice that like the first three are like these three right here, they cancel out with these three right here. So I'm really only interested in the first two of these. So 5 times 4 over 2 times 1, that's a lot easier to calculate. And these cancel, so it becomes 10. Now, let's say I'm doing something larger, right? Like, let's say I'm trying to calculate 10 choose 8. Okay, so at the top, I'm going to have 10 times 9 all the way until 1. And at the bottom, I'm going to have 8 times all the way until 1, and then 2 times 1. So it ends up being, like, it basically ends up being this. So 10 times 9 over 2 times 1, which is just 45. Okay, so do use your cancellation skills. This will help you a lot, especially when you don't have a calculator. All right, now let's go ahead and look at a few problems involving combinations. We did a problem really similar to this, but no worry, like no harm in, talking about the same ideas multiple times. So how many ways can we form a committee of 3 people from 7 people? Okay, so I have 7 people, and I need to choose 3 of them. They're all different people, right? They're not like the same. They're different people. And I have to choose 3 of them. And I don't care, like, it's not like I have like a top guy and then like a second guy. No, like just choose 3 people. So the number of ways to do this is 7 choose 3. And let's just use our formula, 7 factorial over 3 factorial times 7 minus 3 factorial. And this is like 4 factorial, so I'll write it out. 7 times 6 times 5 times 4. So this 4 times 3 times 2 times 1 cancels with this 4 times 3 times 2 times 1. 3 times 2 times 1 is 6, so that's that. And we get 35. So that means there's 35 different ways to choose a committee of 3, a group of 3 people, if I have 7 people to choose from. Okay, so now here's a slightly different problem. How many ways can we choose 4 out of 8 books if 2 specific books must not be chosen together? Okay, this one is a little bit trickier, but let's see if we can go ahead and try it. So let's say those books are A, B, C, and D. Okay. And let's say that, okay, well, no, we need 8 books. So A, B, C, D, E, F, G, H. Okay. So let's say that books A and B can't be chosen together. So maybe an easier way to work with this problem is through an approach called complementary counting. And this is like what complementary counting, like what the idea basically is. So instead of finding like um, the number of ways to choose these books so that like you got to ensure that they're not chosen together, the idea is our answer is just the following. Okay, the number of ways with no restrictions. And then I subtract off the number of ways where those two books are actually chosen together. Okay, so how many ways are there with no restrictions? Well, it's just 8 choose 4 because I'm choosing 4 books from 8. Okay, now how many ways are there to choose these books so that A and B are chosen together? Well, here's an idea, right? Like A and B, I have to choose those and I don't care about the order. So let me just cross these out. So now I have 1, 2, 3, 4, 5, 6 books remaining, and I have to choose 2 other books. So I have to choose like 2 other books. Let's say like maybe I end up choosing like E and I end up choosing like G. But I got to choose like 2 other books from the 6. So the number of ways where A and B are chosen together, like in the 4 books, that is just 6 choose 2. So pretty much our answer is just 8 choose 4 minus 6 choose 2. Okay, and what is 8 choose 4? 8 choose 4 is 8 times 7 times 6 times 5 over 4 times 3 times 2 times 1. Okay, this is 6. 8 divided by 4 is 2. 2 times 5 is 10 times 7 is 70. And 6 choose 2, that's just 6 times 5 over 2, which is 15. So our answer is 70 minus 15, which is equal to 55. So there are 55 different ways. Okay, so a summary of some things we did. We could have solved this problem directly, right? We could have broken it up into different cases. So maybe like only A is chosen, maybe only B is chosen, maybe A and B are chosen. Those are like 3 separate cases, right? Like they never occur at the same time. So we could use those 3 separate cases to solve the problem. But we're like, okay, that seems like a lot of work, right? We want to employ another approach. Like, okay, they tell us, look, we cannot choose these books together. But we're saying, okay, like we're interested in the number of ways, right? So to find the number of good ways, let's just find the number of bad ways and subtract from the total, which is what we're doing, right? We're finding the number of ways where A and B are chosen together, and we're subtracting from the total. So this technique is very powerful, and this is a technique that's called complementary counting. I'm repeating it again, complementary counting. Comple. Okay. And yeah, we did use some combinations and we ended up getting our answer. Okay, this problem, how many ways can we choose 5 out of 10 students if 2 specific students must always be chosen? Okay, let's call these people like I'm just going to call them from person 1 to 10. Let's say we must always choose person 3 and person 6. Okay, so like no matter which 5 people we choose, we always choose person 3 and we always choose person 6. Then we have 8 people left over and we got to choose like the other 3 people. So the answer for this question, this one's actually easier than the last one. The answer for this question is just 8 choose 3. And if we calculate that out, that's, I'll just write it out. 8 factorial over 3 factorial, 5 factorial, which is these dots mean it like continues till 1. Okay, so I have 5 factorial here. It cancels out with this thing right here, which is just 5 factorial. 3 times 2 times 1 cancels with 6. So it turns out the answer for this problem is just 56. 8 times 7, 56. All right, one last problem. For those of you who play poker, this will be interesting to you. If you don't know how cards work, that's fine. I'm going to explain this in assuming no knowledge about how cards work. So I'll kind of like explain how cards work, right? So we have 13 different like values or ranks for these cards. So these are like ace, which is basically like a 1. And then we have 2, 3, 4, 5, 6, 7, 8, 9, 10. Instead of 11, we have a jack. Instead of a 12, we have a queen. And instead of a 13, we have a king. Okay, so they're like kind of ranked in this order. Well, actually, ace is like the highest rank. So it's actually like this, right? So we have 13 different values. Now these values, they can have like a specific suit to them, right? So you can have like a 2 of hearts. You can have a 2 of spades. You can have a 2 of diamonds, or you can have like a 2 of clubs. Okay, and for each of these cards, we have these different like suits, right? We have these different basically labels on these cards. So a full house is a poker hand. It's a pretty rare poker hand, actually. And it occurs when we have 3 cards of the same suit and we have 2 cards of the same suit. Okay, so they're not the same, right? Like, it's not like they're all the same, but it's like I have 3 of the same suit and then 2 of a different suit. So the question is, how many different ways are there to do this? Okay. So I'm just going to just erase some of this stuff so we have more space. Okay, so I mean, there's like a specific card and then I choose 3 of them. And there's a specific card and then I choose 2 of them, right? So I gotta first pick my cards. So let's say that the first card, there's 13 different like ranks for the cards. So let's say the first card, like I choose a 10, right? And there's 13 ways I could have gotten that. And the second card, it's an ace. And then there are 12 different ways I could have chosen that. It doesn't have to be an ace. It could have been like one of the other things besides a 10. Okay, so now out of these like 4 different suits, I have to choose 3 of them for the 10. Okay, so like I have 13 times 12, but I have to multiply by 4 choose 3, and I have I have 2 different aces now, and I have to choose like yeah, sorry. Let me be more clear, right? So I have to choose 3 suits for my 10s. Now I also have to choose 2 suits out of the 4, like 2 of these things out of the 4 for my ace, for my other card. Okay, so I have to also multiply by 4 choose 2. So my final answer is going to basically be the following. It's going to be 13 times 12 times 4 choose 3 times 4 choose 2. And I'm going to, like, I don't know what that is, but like somewhere here, I'm just going to show what that evaluates to. All right, so that's the end of this video. In this video, we talked about permutations and we talked about combinations, and they're both very useful when we're counting the number of ways which we can do something.